So Raman theory. Raman works by taking a monochromatic light, which is just a simple laser, directing it at a sample. Now, the bonds within the sample are going to vibrate upon being excited with the laser energy. The laser is going to be absorbed and reflected back to the detector. And in this process, the energy of that laser changes. And this is what is measured by the spectrometer to then produce the Raman spectrum. Now, the bonds within each mineral are going to be unique, and therefore the energy change when the laser hits the sample is also going to be unique, therefore creating a fingerprint spectrum. The fingerprint spectrum can then be run through a reference library that was constructed from known samples, and this allows you to identify the unknown sample in front of you. For Raman spectroscopy, we use the Bruker BRAVO Raman, which I have with me here. The Bruker BRAVO Raman has a window at the top here, and so the laser is directed through here onto the sample, and so you've got a spot size of approximately 2 millimeters squared. And so as long as the sample is in contact with this window, you're going to analyse the sample of your choosing. It also comes with 2 lithium batteries, one of which is inserted in the bottom here for use. Each battery will give about 4 hours of scan time, and so between the two of them you can generally accomplish a full day's scanning with the instrument in the field. We have a touchscreen here, and so the onboard software allows you to have full control over collecting spectra and also identifying them using onboard libraries of your choosing in the field. So one area in which Raman spectroscopy can really aid is in the exploration of lithium pegmatites. So one of the main problems here is that being able to rapidly identify mineralogy in field is crucial to understanding the mineral system. Now, a problem with pegmatites, a lot of the dominant minerals are varying shades of white, and so confidently and rapidly identifying the mineral phases can sometimes be a bit challenging. Raman spectroscopy can be used to aid in-field geologists for identifying these minerals. So to demonstrate this, here we have 10 white samples, all of which are minerals that can be found in lithium-bearing pegmatites. And by using the Bruker BRAVO Raman, we're going to analyse all 10 and demonstrate that we can quickly and rapidly identify the mineral phases in situ. To demonstrate the use of the Raman, we'll be looking at the identification mode on the onboard software. This mode can be used to perform quick and rapid identification or verification of an unknown sample. To use this mode, you simply select identification, you input a sample name, which for the purpose of this demonstration, I will put S1. On the next screen, it prompts you to turn on the laser. You then align the window here with your sample as best you can and press start. So analysis time of the samples can take approximately between 10 seconds to over a minute, and it does depend very much on the nature of the sample. So the Raman will continue to scan for as long as necessary so the detector has received enough response from the sample to produce a spectrum of sufficient quality to perform library matching. So once it has completed scanning, it immediately displays the top library match for the sample you've just scanned. In this case, it's identified as petalite. If you'd like to investigate further, on the next slide, it will demonstrate the top hits of the library you have selected. So in this case, the top 3 are all petalite, which is rather encouraging that the response it gave us was in fact correct. Further analysis can be done as you can view the spectra. So the top spectra here is in blue, and that is our reference spectrum. So that's the petalite reference spectrum from our onboard library. The bottom spectrum in white is the sample we've just collected, and as you can see in the fingerprint region for minerals, the dominant peaks line up very nicely, and so this supports the fact that it has correctly identified the sample as petalite. So for sample 2, we do the same process. Start. And we see our response as polysite. So this time for sample 3. And we've actually been able to identify a mineral mixture of the 2 mineral phases. So it's identified albite and quartz as being present in this sample. Sample 4. we get the result as eucryptite. So for sample 5, and for sample 5, we get beryl. And for sample 6, and the sample has been identified as albite. For sample 7, we've identified some microcline. And for sample 8, we have amblygonite. And for sample 9, we have spodumene. And for sample 10, we have quartz. So as we've just demonstrated, Raman spectroscopy is great for doing quick verification or identification of unknown samples. It's been particularly useful in the space of lithium pegmatites, as some of the other common techniques used such as XRF or shortwave infrared are not great for those lithium minerals or silicates, and so there's just a bit of a hole in using spectral technology to be able to aid field geologists, and so Raman spectroscopy really benefits us there. You can take this process a step further if you desire, and we can perform further processing on the Raman spectra by extracting specific spectral features to really go that step further into the detail that can be contained within the spectra. And this just helps, say, delineate between your plagioclase from your cave feldspars or between your different micas, for example. So it's great as a field portable technique. It's giving you real-time answers in the field where you need them. So if you've been interested by anything you've seen here today, please feel free to get in contact with us. And there will be a data sheet attached of the results we got from the scanning you have seen that will be provided in conjunction with this video.